Okay.
Eventually.
I mean, if it were entomology class, we'd be right on point. But how are we doing?
Good.
Good. Good.
Got to sleep into that.
Oh, that's nice. I slept in a little bit myself this morning. Yeah. Any questions about anything at all before we continue on with stuff we were doing with divisibility?
Did you want us to turn in the one?
You can just work on that problem.
Okay.
Yeah, that's fine. Yeah. There's something to turn in. I'll explicitly let you know to turn it in. I just wanted you to practice it. Was it okay? Yeah. Okay. All right. Well, let's continue on with this discussion with the GCD being a linear combination of the two things, of the two numbers that you're looking at the GCD for. So started this right at the end of class last time. We start with the set of linear combinations of A and B. We want to make sure it's positive. We're going to use the well-ordering principle to get a smallest element in this set and then show that that smallest element really is the greatest common divisor. So right before we ended class last time, we said that we know that that set's not empty because I can create a linear combination that we can guarantee is positive as long as A and B are not both 0, which is what we're assuming, because I can just use A squared plus B squared. I can use A as R and B as S and do that linear combination. All right, so by the well-ordering principle, S contains a least element. If I can spell contains. We'll call it D. And we will show that D really is the greatest common divisor of A and B. It's kind of strange, at least I think at first glance, this is kind of strange, right? I just created a set of linear combinations, pulled out the smallest possible positive one that we can find, and say, hey, by the way, that's the greatest common divisor. Right? We didn't actually do anything with divisibility. We just created a bunch of linear combinations and picked the smallest thing we could create. So it feels a little bit magical. At least I think it feels a little bit magical, right? Because we didn't actually divide anything. Okay. All right, so there's two things that we need to show in order to show that D is a greatest common divisor. We need to show that it in fact is a common divisor of A and B, and it is the biggest. Showing it is the biggest actually is pretty straightforward. Let's do that first. Let's assume that it really is a common divisor. We'll go back and prove that in a minute. But let's assume that it is a common divisor of A and B, and then we'll show that anything else has to be smaller. Okay? So for the time being, let's suppose that D really does divide A, and D really does divide B. Actually, I don't need to do that part. I don't need to suppose that that's true. Sorry, I lied. I don't need to suppose that part for this point. Sorry. I hate doing that. I hate making you erase your notes, especially if you use ink. All right. Sorry about that. I want to start with, let's show that any common divisor of A and B actually divides D. Okay? And that will show that it's smaller. Okay. So instead of supposing that D divides A and B, let's suppose that we have C divides A and C divides B. I want to show that C is no bigger than D. I want to show that any common divisor of A and B is no bigger than D. One way we can show that is that if something divides A and B, then it also divides D. Right? If something divides another number, at least in absolute value, we know that that's going to be smaller. We talked about that last time. Okay. All right. Well, notice that we've created a linear combination that gives us D, right? So if C divides A and C divides B, why do we know that C also divides D? Let me write this down. So we know there exist integers R and S such that D equals AR plus BS, right? That's how we created D. It was the smallest element in that list, that set of linear combinations.
Oh, because D is the sum of A and B.
Yeah, D is a linear combination of A and B. If C divides A and C divides B, it divides the linear combination. Therefore, it has to divide D, right? We talked about if you divide individual factors of a linear combination, you actually, in fact, divide the entire linear combination, right? So, since C divides A and C divides B, C divides AR plus BS, or C divides D. Therefore, C is less than or equal to D. That last statement, I really mean, you don't have to write this part down, but I really mean that C is less than or equal to the absolute value of D, because it's possible a common divisor could be negative, right? But why do I know I don't need the absolute value bars? In this particular instance, how do I know that I don't need the absolute value bars?
Because A and B is very because because the sum is greater than 0.
Yeah, because I know that I picked a linear combination that's greater than 0, right? Because that's how our set was defined. That's why I don't need the absolute values. All right. So what did we show here? We said that we have any common divisor of A and B is necessarily less than the D we just created. Okay? So if D really is a common divisor, it has to be the biggest of them all. Right? Because any other common divisor is smaller. So our last part here is we need to show that D divides A and, D divides B. We need to show both of those things. Good news is once we want to show one of them, we're going to say similarly it's the other one. Because the proof will be exactly the same. We just have to change the letters. All right, let's suppose not. Suppose D doesn't divide A. We talked about the division algorithm last time. What did the division algorithm give me? I want to divide D into A. So what does the division algorithm give us?
It can be written in form 3k or 3k plus 1 or 3k plus 2.
That was if we had a 3 for the divisor, right? In this case, I want to divide by just a D. So if I take a number and divide it into another, what two things do you get, typically? If you think about doing long division, if I take one number into another, what two things do you typically get? Quotient and remainder, right? So I'm going to get a quotient and a remainder, correct? So by the division algorithm, there exist Q and R such that A is equal to DQ plus R. Right? What has to be true about the R?
Greater than 0.
Okay, well, greater than or technically it's greater than or equal to 0, right? And what else?
Less than.
Less than.
Is it less than D?
Is it less than D? Because D is the thing we're dividing into it, right? All right, if we're assuming that D is not, well, so if D is not a divisor of A, if D doesn't divide A, what has to be true about R now? Can it be 0 if D does not divide A?
No.
No. Okay. So since we're assuming D does not divide A, we actually do have that R is not equal to 0. All right, so the idea here is that we've assumed something here and we want to get a contradiction. So this is where the contradiction is going to come in. What we're going to do is we're going to write R, now that it is positive. R is now a positive number, right? It's not 0. We're going to write R as a linear combination of A and B. That's what we're going to get to, okay? So the first thing I'm going to do, write it this way. I'm going to write it as, pardon me, write it as A minus DQ. We have something we can substitute in this equation. Which of the A, D, and Q, what is something that we can substitute in for?
You can substitute D.
And what is D equal to?
AR plus BS.
Good. And now if we rearrange a little bit, this is what A times 1 minus QR plus B times a negative SQ. I do a little bit of algebra. Shockingly enough, doing algebra in an algebra class. Call me crazy.
Crazy.
Thanks. All right, so now how have we expressed R? So here's my A, here's my B. How have we expressed R? Yep, a linear combination of the A and B. What else do we know about R? It is greater than 0. So if I go back up to my definition of my set, where does it say R lives? S is the set of all linear combinations of A and B that are positive. So where does R live? In S, yeah. But what we assumed that R was greater than 0, but what else do we know for a fact that R is? What's the other condition on R? It had to be greater than or equal to 0 and less than D. And how did we pick D? How did we come up with a D to start with? Scroll back up here. How did we pick D to start with?
It's the least element of S.
Yeah, it's the least element of S, right? Is that a problem? D is the least element of S, but I found an element of S that's smaller. Is that a problem? Yeah. Okay. This is a contradiction. Thus, R is 0 and D divides A. You can do the exact same proof to show that D divides B. No, it's not exact same proof. Your letters will be slightly different, but it's the same exact idea. You'll divide, assume that D doesn't divide B, get a quotient remainder. Your remainder is non-zero. Write as a linear combination, then it'll be smaller than D again. Okay. So I'll just write similarly. D divides B. Which is what we needed, right? We already showed that any common divisor is no bigger than D, and now we've shown that D is a common divisor. Therefore, D is the greatest common divisor. that okay? So to illustrate how this can help, let's look at number 25 on page 16. So 25 says that if there exists U and V such that AU plus BV is 1, then the GCD of A and B is 1. That's actually part A. We'll go part B here in a second. So rather than write a whole bunch of stuff down, let's just think about why this has to be true. We just said that we can write the greatest common divisor of two integers as the smallest possible linear combination, right, that you can possibly get. Right? We can do the set of all linear combinations. The greatest common divisor is the smallest positive linear combination that you can get. Well, does any positive linear combination get any smaller than 1? No. Okay. So since AU plus BV equals 1 is the smallest positive linear combination possible of A and B. Oops. We have that the GCD has to be 1. Now, this is a special case. The reason why it's a special case is because the linear combination actually is 1. Okay? Just because I have a linear combination that gives me a number doesn't mean that that number has to be the GCD. Okay? So that's actually part B of this. Let's, by example here, say, well, I know that, let's do 3 times 4 minus 5 times 2. That's a linear combination of 3 and 5. That gives me 2 in this case, right? Yeah. Is 2 the is 2 the GCD of 3 and 5? No. So just because I have a linear combination that gives me a number doesn't mean that that number is the GCD. Now, we can say something about the number. It may not be the GCD, but since it's a linear combination of the two numbers, it has to be divisible by the GCD. Okay. So if D is the GCD and we have A, I'll call it C, equals AR plus BS, then certainly D does have to divide C by the same properties we've been talking about. So you can do a linear combination. You can get a linear combination, whatever the number comes out, you know the GCD actually has to divide it. So it might eliminate some possibilities. But unless the linear combination you formed is equal to 1, you don't necessarily know that GCD is that linear combination. It could be smaller. So trying to find the GCD by looking at linear combinations is probably not the most efficient method. There is a nice method for figuring out the GCD. It's called the Euclidean algorithm. If you had discrete, you saw the Euclidean algorithm. If you're indiscrete, I'm certain you will see the Euclidean algorithm. It's a slick little way to do the GCD quickly. Just to mention, I'm not going to go through, I'm certainly not going to prove it, or I'm not going to spend time on doing problems with it, but I'll just remind So if you want to do the GCD of A and B, divide the smaller into the bigger. Then take your remainder that you just got and divide again. Oops, it's a 1 and a 2. I don't know why I changed my numbers. Then do it again. Just keep dividing your remainders smaller and smaller. Eventually, since your remainders always get smaller, this eventually has to stop, right? So eventually you have to get to something that gets evenly divisible. It has to stop. And so that this number here is your GCD. So then it's a nice algorithm. It goes much faster than other algorithms that you have for checking GCDs. You just have to do repeated divisions. The reason why it works is that if you have a common divisor of A and B, then it has to divide R1. And then if you have a common divisor of B and R1, it has to divide R2. So on down the line, any common divisor has to divide Rn. And since Rn divides Rn, that's an Rn minus 1. I don't have an equal one there. Sorry. Got an extra line in there. This last statement says that Rn has to divide Rn minus 1. If it divides Rn and Rn minus 1, it has to divide Rn minus 2. Work your way back up, it has to divide A and B. So it has to divide both A and B, and it's also the biggest. So it really is your GCD. That's why it works.
Same method you transfer things to binary.
Oh, doing repeated divisions and picking off the remainders. Yeah, that's the same type of process. You're right. Except in that case, you're doing repeated divisions on the quotients. This one, you're doing repeated divisions using your dividing into the remainders. So it's a similar process, but not quite. Yeah. But it's like I said, it's super nice. So you could do something like, since we're already talking about it, I'll go ahead and do an example. Not that this is all that important for what we're going to do later, but I'll go ahead and mention it. Let's say you wanted to find the GCD of 35,828 and 4,296. So, just making it up. I picked something that has a GCD definitely bigger than 1 because 2 divides both of them. So again, if you were to do this in a grade school fashion, there's a couple of ways you might do it. I need to write down all my factors of the 35,828, write down all my factors of 4,296, and pick out the biggest. The other way would be prime factor both, and then pick out the smallest power for each prime that's in there, and that would be your GCD. There's a couple of ways to do it. Neither of those are very efficient. Okay. In this one, I take the 35,828 and find a quotient and remainder. And since I don't have a calculator up easily, if I do 35,828 and divide it by 4,296, we get 8 times 4,296 plus 1,460. I'm assuming you can divide and find remainders. So now we take the 4,296 and divide it by the 1,460. We get 2 times 1,460 plus 1376. That one I can divide without a calculator. That is what, 84? Oops. 16 times 84 plus 32. What, 32 times 2 gives me a 20. I know I'm doing it quickly. Eventually I'll get there. Hey, I got there. Cool. All right. In any event, this is your Euclidean algorithm. Notice it's very repetitive. You can, if you've done programming and you have done recursion, you can write this recursively really quickly. It's a quick recursion, right? Because you're just replacing the two numbers as you go with the remainder. You just have to calculate the remainder and then replace, right? Again, it has to stop. Your remainders cannot be negative and they have to get smaller at each step. So the process has to stop. The algorithm has to terminate. Okay. So here it terminated when we got to a remainder of 4. So this 4, this is your GCD. Notice that you didn't have to do any factoring at all. You have to do some arithmetic, but you don't have to do any factoring. For those of you who had discrete, does that look familiar? Yeah. It's a pretty straightforward process. It's not hard. And again, it's nice because you don't have to do any factoring at all to get it. Any questions on that at all? All right. Okay, let's look at one other example here that uses the fact that we can write a GCD as a linear combination. So this theorem says that if A divides BC and the greatest common divisor of A and B is 1, then A must in fact divide C. Now we haven't gotten to it yet. We'll do that here in a minute when we get to the next section. But this kind of makes sense if you think about it in terms of primes. Anything that divides A, so if you think about it in terms of primes, if anything that divides A would have to divide one of these two things, right? Well, if the GCD of A and B is 1, anything that divides A can't divide B. So it'd have to divide C. You don't have much of a choice, right? If you think about it in terms of breaking it into pieces. We haven't done that yet, so we'll do the proof a little bit more straightforwardly. Again, now we have the GCD of A and B is 1. So what we just proved a little bit ago, how can I write 1? How can we always write the GCD of two numbers? Yeah, the linear combination piece is what we want, right? So since the GCD of A and B is 1, there exist, give me two letters, I don't care what they are, as long as they're not A, B, or C. R and S? You'll use R and S? Okay. I was trying to get something different than R and S. That's okay. There exist two integers R and S such that AR plus BS, and there's a bunch of BS, equals 1. Yeah, I always thought that getting a BS degree was kind of appropriate. There's the joke of BS and then MS for Master of Science for more of the same. And then PhD is piled higher and deeper. So,
BS takes you places.
what's that?
BS takes you places.
It's right, it does. All right. So I want to show that A divides C. Okay. So I need to show that I already know that A divides the product of the two, certainly. But let's do the following. Let's start with C. What can I multiply C by and not change anything? Not a trick question. What can I multiply C by and not change anything? By 1, right? So I can write this as C times 1. But do we now have a clever way to rewrite 1? Yeah. I could replace the 1 with AR plus BS. And I'm going to rewrite this slightly as A times CR and then BC times S. Distribute my C through, but rewrite it in that fashion. Look at this first term. Remember, we're trying to show that A divides C, right? Do I know that A divides the first term? The first term of that sum? Do we know that A divides the first term of that sum? Yeah, what's the multiple of A, right? Do I know that A divides the second term? Yeah, that's what we're assuming, right? Okay, so we have certainly A divides A, period, and A divides BC by assumption. So A divides what? If a number divides two pieces, it divides the sum of the linear combination again, right? So A divides ACR plus BCS, but another name for ACR plus BCS is C. That okay? Pardon me. All right, so there's a couple of problems I do want you to turn in for next Thursday out of this section. This is number 17 and number 23. This is on page 16. One of them uses the result we just proved. The other one, I want to remind you about proof by induction. So that's why I'm assigning those two in particular. All right. Well, let's go on to the next section. Bless you. Bless you again.
Thank you.
I've already alluded to, why can I not spell factorization? I'm getting to the I too fast. I already alluded to primes. So let's do a little bit of stuff with primes. Pardon me. So we can do primes. There's other structures in which there are primes. We're going to be talking about primes as far as integers go. But in order to be a prime, you need to make sure that you don't have anything that divides the number besides the units, right? We already talked about that in order to be a unit is something that you can always divide by, right? No matter what, you can always divide by a unit, the things that we call those invertible elements. And we'll do more with units as we go farther along the semester. But in the integers, there are only two numbers that you can always divide by no matter what, and those are 1 and -1. Okay? So when we talk about factorization, we usually ignore the units because I can always stick those in or move them out no matter what. Okay? Because if I can always divide by it, I can always take that thing and then times its inverse, multiplicative inverse, and I get a new factorization. So the units aren't very interesting in terms of factorization. Okay? So for primes, we always throw out 1 and -1. And usually when you talk about primes, you think about the positive ones, but technically if you stick a negative on there, it's still prime. Okay. All right. So as a definition, an integer P with P not equal to plus or minus 1 is prime if its only divisors, are plus or minus 1 and plus or minus P. Your book also in the definition throws out 0. There's a technical reason why your book throws out 0, but according to this definition, if I say the only divisors are plus or minus 1 or plus or minus P, I can divide anything I want into 0, right? So it's going to have more of the divisors than just itself. So I don't really need to throw in 0 into this definition. However, there is a reason why your book puts in 0 in this definition, because there's an alternative way to define prime more abstractly. And when you define it more abstractly, 0 becomes prime. Okay. Well, we actually will talk about that later. Not today. Not today. Later on the semester, we'll talk about that. You actually use this fact, by the way, when you solve equations. When you solve something like x squared minus 5x plus 6 equals 0, you multiply, you factor it, and then you set each factor equal to 0. That has to do with 0 being prime, just as a for instance. Okay. So you actually use that, and it's actually important. It's just not important here. So I'm going to skip it. Okay. All right. Enough of that. So one of the things your book talks about is the positive and negative pieces, which I'm not going to worry too much about that. What I am going to worry about, one of the best properties of being prime, is that if I know a prime divides a product, then it has to divide one of the pieces. Oops, not and, or. This is one of the important properties of being prime. If I have a prime divisor of a product, then that prime actually has to divide one of the pieces. Okay. I like doing this proof for a couple of reasons. One is that, again, it's a nice property of primes, and illustrates the importance of primes. The other is that it's also a very, very good example of a proof by cases idea. I'm trying to show that one or the other is true. Either P divides B or P divides C. Could divide both, but it has to divide one of them. So when we have a situation where we try to prove an or statement, typically we assume it doesn't happen for the first one and then prove it has to happen for the second one. Okay. So this is one of the reasons why I like doing this particular type of proof, is it gives that proof technique. So if P divides B, we're done. So suppose that P doesn't divide B. If P does not divide B, what is the greatest common divisor of P and B? 1. Good. Period. Right? There's only 2 divisors, if we think about it being positive. There's only 2 divisors of P, one in itself. And we could do the negatives. Like I said, I'm not going to worry about the negatives too much. Okay. But that's it, right? That's all you get. And if P doesn't divide B, then their GCD has to be 1. What did we just prove a minute ago? If a number divides a product and the GCD of A and BC is 1, then A divided C, right? Isn't that the exact same setup we have, except that instead of calling it A, we called it P? Yeah. So by theorem, or thumb 1.4, always abbreviate it, by theorem 1.4, we have P divides C. Not a very long proof. Another reason why I like it. It's not a very long proof. But it does illustrate the property that I mentioned about the proof technique that I mentioned about kind of a proof by cases idea, if you will. Is that okay?
What number of proof is this theorem?
This is, oh, did I not put it on my theorem? I'm sorry. It's the next one. All right.
I just want to make sure.
Yeah. Okay, so let's do a corollary to this, which is 1.6. This is, I want to do this because I want to give an illustration of inductive proof again, but this one I don't really have to do induction necessarily, but it's a nice little idea for induction. So the corollary is that if P is prime and P divides A1, A2 up to A, the product of A1, A2 up to AN, then P divides A sub I for some I in 1 to N. Not 1 to N, that's right, 1 is fine. All right, so let's do this by proof by induction. So remember, inductive proof, you need a basis step and an inductive step, right? There's two pieces to every single inductive proof. In this case, our lowest value of n that we're actually interested in is 2. Because I actually want a non-trivial product there. I will actually multiply at least 2 things together. So our basis step, n equal to 2. Well, our basis step for n equal to 2, isn't that what we just proved? That was theorem 1.5. Just calling B and C A1 and A2. It's literally what we just proved, isn't it? So our basis step is theorem 1.5. Again, your basis step, usually in a proof by induction, the basis step is the easier one. You want to plug in the n value that you start with and just verify that you have a true statement. Usually that's the easier of the two pieces to prove for an inductive proof. We might argue whether or not that was the easier one of the two in this case, because the other one's not any worse. There are instances where the basis step is hard, the inductive step is super easy. Doesn't happen very often, but it does happen. All right, so then your inductive step will assume that the given statement, the statement that we have, is true for all m up to a certain point. We started at 2. We're going to assume that it's true. What we're assuming is that we've made the proof work starting somewhere and going up until a certain point. And then we want to show that we can get to the next stage. So again, you heard me talk about induction before. I liken it to building a building. First thing you have to do is make the foundation. Once I make the foundation, I can make the first floor. Make the first floor, I can make the second. Once I make the second, I make the third, and so on down the line. Okay, so that's exactly what we're doing. We're assuming we've built n floors. We're going to build the n plus first floor. Okay? All right. So in this, we're going to suppose that P is still prime. And P divides a product of n plus 1 things. The number that's changing is the number of factors that we have, right? Okay. Well, let's be clever a little bit and put in a set of parentheses here. Instead of considering it as n plus 1 things, how many things did I just consider it as? By putting those parentheses in there. 2, right? Have we made a proof about 2 things? Yeah. So by the basis step, if you will, or the inductive hypothesis, either one, I'll say by the basis step, P divides A1 or P divides A2 out to AN plus 1. Right? Now how many factors are in the second piece? N of them. And by the that falls under our inductive hypothesis, right? So this is pretty indicative, again, of any proof by induction. I want to break my inductive step down so that I can actually see the inductive hypothesis work, right? I want to be able to use the inductive hypothesis. The inductive hypothesis, I need n factors. So the first thing I did is I broke up my statement so that one of them had n factors that I could use it, okay? So by the inductive hypothesis, which again, the inductive hypothesis is this piece that I'm putting in brackets here. That's what we mean by the inductive hypothesis, the assumption that we're making. Okay. By the inductive hypothesis, we have, well, we still have the P is divides A1, or the inductive hypothesis now says that I can take my P and has to divide one of those. So I'll write it as P divides A2 or P divides A3 ... or P divides AN plus 1. That verifies the inductive step, right? We proved the theorem for the inductive step. This is what we wanted to do, right? We have to divide at least one of them. Okay. So, therefore, by induction, basically I'm just restating the theorem. If P is prime and P divides a product, we have that, or I'll say then, P divides AI for some I from 1 to n for all n. Again, not a big end-all be-all of theorems, but I did want to remind about the how induction works. Induction also gives you what we refer to as the fundamental theorem of arithmetic. I'll let you read the proof. Fundamental theorem of arithmetic just says that every integer that's not a unit, and not 0, every integer that's not a unit can be written uniquely as a product of primes if you ignore the plus or minus parts. And so every positive integer greater than 1 can be written as uniquely as a product of primes. I'm not going to spend the time to prove it, but that's what the fundamental theorem of arithmetic says. You get lots of fundamental theorems in math, right? Fundamental theorem of arithmetic talks about prime factorization. Fundamental theorem of algebra talks about how many zeros there are of polynomials. Every polynomial of degree n has exactly n complex roots, counting multiplicities. Fundamental theorem of calculus. Fundamental theorem of ordinary differential equations. Fundamental theorem of finitely generated abelian groups is an algebra theorem. There's lots and lots of fundamental theorems.
The last one had words.
I know the last one had words, didn't it? Yes, I know. Finitely generated abelian groups. We'll talk about abelian groups this semester. Finitely generated isn't a hard thing either.
There's just the word in the middle.
The abelian?
Yes.
Yeah, named after Niels Abel, who's a mathematician.
We'll get
Norwegian mathematician, if I remember correctly. Yeah, Niels. I think his first name is Niels. No, it's Abel. All right. In any event, let's see if we can do a proof or two involving some primes. Pardon me. So let's look at, say I picked a couple out here. This is number 6 on page 22. It says if P is prime and P is divided by 10, is divided by 10, then the remainder is 1, 3, 7, or 9. The prime needs to be bigger than 5, by the way. Because if I divide 2, 3, and 5 by 10, I get a remainder of 2, 3, and 5, respectively. So your prime needs to be bigger than 5. It's more interesting when it's not 5. Or bigger than 5, I should say. I didn't write that down. The problem did. I didn't write it down. All right, if I divide something by 10, how many possible remainders are there? Not a trick question. If I divide by 10, how many possible remainders do you have? 9. I think you get one more than that. 10, because you start counting with 0.
Oh.
Yep. The possible remainders are 0 through 9, so there's 10 possible ones, right? So if I divide by 10, there's 10 possible remainders, so we need to throw out 6 of them. Right? Okay. We should be able to throw out 1 easily. If I divide the prime by something other than 1 and other than the prime, what remainder can you throw out automatically? If I take a prime and throw out 1 and throw out the prime, what remainder doesn't work? 0, right? Because it doesn't go in evenly, right? So I can throw out 0 easily because P is prime, 10 is not, right? So I'm dividing P by something other than 10, other than 1 and other than itself, right? Okay. So first, since P is prime and 10 is not P, the remainder can't be 0. Okay. Let's see what else we can throw out. Let's write P this way. That's division algorithm, right? I know that I can find a Q and R that does that. Now look at what we're trying to throw out. Let's ignore the 5 to start with. Let's see, get rid of the rest of the evens. Why do we know that 2, 4, 6, and 8 can't be possibilities?
Can't be prime if they have 2 as a factor.
Yeah, so notice that if your remainder is 2, 4, 6, or 8, what divides the remainder? 2. What do you say about that? Also divisible by 2, right? So what would happen to the prime then? Also be divisible by 2, wouldn't it? Right? Is there anything different about 5, by the way? If this remainder is a 5, what can you say about the 10? Well, also divisible by 5, which would make your prime divisible by 5, right? So if your remainder is 2, 4, 6, no, I'll write it as 5 just to keep them in order. 2, 4, 5, 6, or 8, then I'll write it as the GCD of 10 and R is greater than 1, right? It's either 2 or 5. And the GCD of 10 and R would divide P, which is a problem. And that's pretty much it. So the only possibilities are 1, 3, 7, and 9 for the primes. Which makes sense. I mean, this is probably something you already know. If you're looking for prime numbers, you know it can't end in a 5. And that's exactly what the remainder would be. If you divide by 10, it's just the ones digit. Right? We know that if a number ends in 5, it's divisible by 5, so it can't be prime. Which leads me to a funny story. Well, at least it's funny to me. Probably not funny necessarily to you necessarily. But I work with a buddy of mine, lives in Minnesota now, but we invited him to give a talk to a bunch of high school students in the area when I worked at a previous institution. Came down, gave a talk. He was talking about prime things. Put this gigantic number on the overhead projector back when we still used overhead projectors and transparencies and all that good stuff. And said, if you can tell whether or not this is prime, I will offer you, I can't remember, like $1,000. The reason why he said that was because there was a challenge out for that particular number to say that if you could show it was prime or not, then there was a $10,000 reward for it. Okay. Problem was that if you looked at the very, very end of the slide and cut off the number he had on the slide was headed in a 5.
Oh.
It was really funny. It was funny to me. So, anyway, like I said, you can look at this particular one and know that there's no way it could end in a 5 because, again, when you divide by 10, it's the ones digit that pops off for the remainder. All right, let's do another one here. And this actually illustrates the corollary that we talked about a minute ago. This is number 15 on page 23. This one says that if P is prime and P divides A to the N, then, well, it actually asks, is it true that P to the N divides A to the N? It gives you a hint, but I think there's actually 2 ways to think about this. One involves the corollary that we did. The other involves factorization. There's 2 ways to think about it, personally. There might be more, but at least when I look at this problem, I think of 2 different ways you can get to the same answer. Let's do the corollary way first, only because that was what they said in the book for hint, use the corollary. Okay? Right? So remember what the corollary said. Let me scroll back up. If P is prime and P divides a product, then P has to divide one factor in the product. Right? So go back down here. Do you see P dividing a product by assumption? Yeah, this first part right here says P divides A to the N would be P divides A or A, right? You agree with that? By the corollary, what does it say P has to divide? The corollary said if it divides a product, it has to divide one of the factors. So what does it say that P has to divide? Even more specifically, what does it say P has to divide? Are the factors different here? No. So what does P have to divide? A, right? So the corollary tells us that P divides A. Well, if P divides A, just raise both sides, if you will, to the nth power, right? So this would imply that P to the n does divide A to the n. That makes sense? The other way I think about it, the other way I was thinking that you could think about it is that we know that A to the n is a product of, A is a product of primes, right? By unique factorization. Yeah. So if I started with A was, I'll say Q1 to the N1, Q2 to the N2, and so on up the line. I probably should have used a different letter there than N. What happens when I do A to the N? I had N1 and then an N. That's why I said I probably should have used a different letter. Yeah. And then same way up the line, right? I would just have the N's on each of these. Right? But notice that I would have each of those in particular, if I look at the individual pieces, like the Q1, N1, and N, I could actually pull that N to the inside, right? So when I take A to the N, those primes just get raised to the nth power. Doesn't matter what the exponent is on them, right? If P divides A to the N, P has to appear in that list, but really I get P to the N has to appear in the list. So that's why I said I think we could have also thought about it a little bit with the unique factorization of the numbers. So, in any event, I think the other way was shorter. I just thought there was two different ways you could think about it. Like I said, there might be more than two ways, but that was the two ways I thought about. All right. Any questions on primes at all? I do want to give you one to practice. You don't have to turn this one in. 18 on page 23. This one is asking you, the first two are just looking to see if you can find counterexamples or not. Then the second one, you actually should be, or excuse me, the first two are find counterexamples or not. The third one actually is true. You should be able to prove it. Okay. All right. So in the time we have left here today, I'm going to skip ahead to an appendix. Again, it's something that we're going to need more and more of as we go through. And it's something we touched on, or you will touch on in discrete, that probably we didn't spend as much time as at least I would have liked to do, and that is equivalence relations. This is in Appendix D. The reason why I want to do this first is because the first section in Chapter 2 is an example of an equivalence relation. It's a specific example, and we're going to play with that particular specific example a lot, but we're going to come back to this general idea later. So I want to go ahead and talk about the general idea some, and then be able to expand on it later. Okay, so that's why I'm going about it this way. So really, when you have equivalence relations, what you really want to think about is you're just treating things like they are equal to each other. Okay? Even if they're not necessarily equal to each other, we treat them like they are. Okay. The best example that I can give you of an equivalence relation that's not just equality is your fractions. And I'm going to write it on the board, even though I know that I have it on the screen there. But remember that in fractions, there's lots of things that I can represent to mean the same thing, right? 1/2 is the same thing as 2/4, right? As a fraction. Okay. When we talk about equivalence relations, a relation is just a set of ordered pairs. So if I want to think about these as ordered pairs, now I don't see fractions anymore, right? I have a 1, 2, and a 2, 4. Right? Now I don't see equals anymore. I see ordered pairs, and those are not the same ordered pair, right? When we make this equality, what we're really doing is an equivalence relation saying, I want to treat 1, 2 and 2, 4 like they're exactly the same. Okay? That's the idea. And we typically use a tilde for related to, and I'll write that down in a second. But that's the idea. You're used to doing this, right? But when you're doing this, you're really doing this in an abstract sense. All right, so again, I want to think about, in terms of equivalence relations, we want to think about it making it equal. What does it mean for two things to be equal? Well, you know from your equality stuff is that everything's equal to itself, right? If one thing's equal to another, then vice versa is also true. If you have one thing equal to another, then the first and the third are equal to each other, okay? Those are kind of your three fundamental properties of equality, and that's exactly what we say for an equivalence relation, okay? So as a definition, we're going to let R be a relation on a set A. Now, what do I mean by a relation on a set A? This means that R is a subset of A cross A. And if I need to remind what A cross A is the set of all ordered pairs that you can make by using elements from A. Remember Cartesian product. When you write A cross B, it means the first component of your ordered pair comes from A, and the second component comes from B. But if I do A cross A, they're both coming from A. So for example, R cross R graphically is your plane, right? X is a real number, Y is a real number, and you get the plane. Okay? So when we say a relation on a set A, I just mean a subset of all the ordered pairs that you can make by using elements from A for your first and second coordinates. Okay, that's all I mean by relation. For equivalence relation, then R is an equivalence relation. Oops. If I should say an equivalence relation on A if three properties are met. And they're the exact same properties that we said we wanted for equality. The first one would say that I want it to be reflexive. This is what a reflexive means. Everything is equal to itself. If I want everything to be equal to itself, then I need A comma A to be in the relation for no matter what. Okay. We also want it to be what's referred to as symmetric. Oops, I need to say in R. Forgot to say where that lives. If I start with A, B, and R, then B comma A is also in R. That's symmetric. And then the last one says that if A, B, and B, C are in R, then AC is also in R. And that's what we refer to as transitive. I've written these as ordered pairs. Notice that my ordered pairs are component, comma, component. When I wrote this example on the board, I didn't write this. Okay. So this is what I wrote for the relation symbol. If I wrote it in terms of ordered pairs of things from the set cross itself, I would have a goofy looking ordered pair. That's gross. I think that's gross, right? I've got an ordered pair made up of two ordered pairs. That was a little ridiculous. So even though this is how it's defined, usually we use the tilde notation, makes things a little bit simpler, right? Okay. So for this one, if I just rewrite that in that notation, your 1 becomes A is related to A for all A in A. The second one becomes if A is related to B, then B is related to A. And the third one becomes if A is related to B and B is related to C, then, A is related to C. And that's a little less gross. At least I think it's a little less gross for the notation. Okay. Now, if there's any question about what the relation is, you will also see sometimes they'll put a little subscript of an R on the tildes if there's any question about what the relation is. Or if you're doing a problem where you've got two different relations and you're asked, is this one a relation an equivalence relation? Oh, is this one? Then they might put the little subscripts on there. But if there's only one relation, there's not a lot of point to put the subscript on there, and then we understand which one it's coming from. I just want to mention that sometimes you'll see that. Sometimes we call equivalence relations congruence relations. And we will actually use the word congruent when we do modular arithmetic next Tuesday. Okay. Let's see if we can go through a quick example of showing that something is an equivalence relation. I'm going to ignore that for the time being, since we're meeting as a class here for the next 2 minutes. Anyway, so let's look at, this is number 4 on page 534. So they walk in. If they're looking for a professor, they're not going to find them. Hi. So we're not working. We don't have the math center with me. Are you making for class? Yeah. Okay, I will be. I'm teaching class right now. I will be done here in a few minutes. Yep, you're fine. Yep. All right. So let's look at number 4 real quick. So this one says that if M and N are lines, and we define M related to N if and only if M is parallel to N, is this relation, and we do sometimes just use the tilde all by itself to denote the relation, is that an equivalence relation? So let's just talk about whether or not this would be an equivalence relation. Part of it depends on what you mean by parallel. So let's do the symmetric and the transitive first. So if line M is parallel to line N, is it true that line N is parallel to line M? Yes. So we definitely need symmetric, right? Without any question. Okay. If line M is parallel to line N, and line N is parallel to line R, is it true that M is parallel to R? Yes. So that would be transitive, right? So the question is whether it's reflexive. What does reflexive mean in this context? And I know we were just about out of time. What does reflexive mean in this context? They'd be the same line. The line has to be parallel to itself, right? That might be a question that you might want to think about for a minute of, do I really want a line being parallel to itself? think about it algebraically. How do you tell if two lines are parallel? Same slope. Does a line have its own same slope? Sure. So perfectly fine to have a line parallel to itself. So usually you think of lines being parallel as they don't intersect. That definition doesn't work for being parallel to itself, does it? But same slope does. Okay. So there really is a question there, is a line parallel to itself? And generally speaking, we say yes. But if you think about teaching geometry in the future, there is a question between those two things, right? Is it parallel to itself or not? When you think about it intuitively, they don't intersect. Well, certainly a line intersects itself. It's the same line, right? But then you also say parallel lines have the same slope in algebra class. Well, a line has the same slope as itself, so it's parallel to itself. Right? So kind of a hard concept. Right? So something to think about for the two math ed people in the room. And the third former math ed person in the room. All right. Well, have a good one. We'll talk more.